11.7 Strategy for testing series. It is not wise to apply a list of tests in a specific order until one finally works. It is better, instead, to classify the series according to its form. So here are strategies here. I'm going to list them. Number one, we need to recognize what kind of series we're dealing with. So if the series is a p-series, if the series is a p-series, meaning it looks something like this, 1 over n to the p, we know that the p-series is convergent if p is greater than 1 and divergent if p is less or equal than 1. So that's the first thing we look. We classify what kind of series we're dealing with. If you recognize it's a p-series, then use the p-series, what we know about. If the series is geometric, series of this type, a r to the n, we know it is convergent. I should write this here. It is convergent if the ratio absolute value is less than 1, and divergent if r greater or equal to 1. We already know this. Some algebraic manipulation may be required first to bring the series to this form. Number 3, if the series has a form similar to p-series or geometric series, one of the comparison tests should be considered. So if it's similar, if the series has a form similar to p-series or geometric series, use comparison test. So let's list those two tests. There are two. So we have comparison test, where we compare with a famous series what we know about. So we have two series, a sub n and b sub n, and they have to have positive terms, very important. These comparison tests are for series with positive terms. So A, if sigma b sub n is convergent, and we have this inequality a sub n less or equal to b sub n for every n, then the smallest series, so if the bigger one is convergent and we know about it's either p-series or geometric series, then the smaller one is also convergent. We already have those tests, so that's kind of a review here. B, if the sigma b sub n is divergent and we have this inequality that a sub n is greater or equal to b sub n, in other words, the smaller one is divergent, and that's for every n, then the bigger one is also divergent. So this is how it goes: divergent, divergent. Here, convergent. This is the inequality, convergent. And the other comparison test, we call it the limit comparison test. So again, we have two series, and they both have positive terms. They have positive terms. If the limit of the ratio a sub n over b sub n when n goes to infinity is some number c that is finite and positive, then either both converge or both diverge. Then either both converge or both diverge. So again, we're comparing with a series that we know whether it's convergent or divergent. For example, harmonic series, we know it's divergent. The P series, we know when they're convergent, the geometric series. Note, these tests apply only to positive terms. But if your series has some negative terms, then we can apply the comparison test to the absolute value of the a sub n and test for absolute convergence. So let me make that note here. Note, these tests so far, the comparison tests apply only to positive terms. But if our series has some negative terms, then we can apply comparison tests to this series with the absolute value and test for absolute convergence. And we know if a series is absolutely convergent, then it is convergent. Number 4, if you see at a glance, that the limit of the nth term is not 0, then use test for divergence. So let's recall this test for divergence. It's one of the first things we learn in chapter 11. Very simple. If the limit of the nth term when n goes to infinity does not exist, or if this limit is not 0, then we have divergent series. Number 5, we're listing strategies here. If the series is of the form, either sigma -1 n minus 1 b sub n or sigma -1 to the n b sub n and from 1 to infinity. In other words, we have alternating series. Then alternating series test is obvious. Alternating series test is obvious. So let's recall that. Alternating series test. So first of all, if we have a series of that form, -1 to the n minus 1 b sub n, or you can expand it b1 minus b2 plus b3 and so on. Now the b's are positive, okay? And if that series satisfies these two conditions, first of all, it has to be decreasing. That's what that means, decreasing. And the second condition is that the limit of those b terms is 0. Remember, they're positive. Then the series, the original one, is convergent. All right, So alternating series or negative signs, use the alternating series test. Number 6, series with factorials or products constant to an nth power, use ratio test. But especially if you have factorials. So let's recall the ratio test. I would say algebraic functions. First, if the limit of the nth term to the n plus 1 term to the nth term absolute value is equal to some number L less than 1, then our series is absolutely convergent and therefore convergent. So it's very, very strong test because it gives you absolute convergence. If that limit is L, some number L greater than 1, or the limit is infinity, and in all those limits n goes to infinity, then our series is divergent. And third case, if that limit is exactly 1, then the test is inconclusive. That means you have to use another test. The series can be the divergent or convergent. Number 7, strategy. Continue with strategy. Number 7, if your nth term has nth powers, not a constant, but the term has nth powers, such as you have something like this, then use the root test. That should be obvious. And let's recall the root test. Very similar to the ratio test. 3 cases. If the limit of the nth root of the absolute value of a sub n is some number L less than 1, then our series is absolutely convergent and therefore convergent. Number 2, if the limit of the nth root absolute value of a sub n is some number greater than 1, or that limit is infinity, then we have divergence. Number 3, if that limit is equal to exactly 1, then test is inconclusive. You already have those tests in your notes. This is a review from everything in chapter 11 so far, just listing the strategies. Number 8, if the nth term can be represented as a function where integral from 1 to infinity of that function where the integral, which is improper, is easily evaluated. You might have to use strategy, substitution, integration by parts, but easily evaluated, then use the integral test. But you have to check the hypothesis. Check hypothesis. So let's list that test right now. Integral test. We have conditions. So first, f has to be continuous, has to be positive, and it has to be decreasing. Not everywhere, but from 1 to infinity. and you have this correspondence, the nth term is a function, then the series, sigma a sub n from 1 to infinity, is convergent if and only if the integral is convergent. In other words, if you can evaluate it and get a finite number, it's convergent. If that integral is infinity or does not exist, then it's divergent. So let's look at some examples now. We're not gonna decide convergent or divergent, we're just gonna decide what method we're gonna use for each example. Example 1, I have sigma n minus 1 over 2n plus 1, and n is from 1 to infinity. You don't even have to expand it, just look at the nth term. Let's write the nth term and think. If we let n goes to infinity, it's very, very easy. Divide both numerator and denominator by n, and you get 1 minus 1 over n, 2 plus 1 over n. Now we know what happens when n goes to infinity. That goes to 0, that goes to 0. So that's equal to 1/2, which is not 0. So if the nth term does not go to 0, use test for divergence. Okay, so it seems like this is divergent series. Example 2. I have sigma of some algebraic function n to the third plus 1, and is from 1 to infinity. The denominator is polynomial. Okay, so we have algebraic function. Let's just write down what it is. A sub n is equal to, I'll just have to copy it. And I'm going to say algebraic function. Algebraic function is a combination of polynomial and rational functions using square roots and other operations. So we can compare here with some p-series or geometric. In this case, it's going to be a p-series. Let's take the leading term here of the numerator. That'll be n to the 3/2 or square root of n to the third. And the leading term of the numerator is this. So this is what we're going to compare with. Our b function would be n to the 3/2 over 3n squared. So these are the leading terms, or the dormant or the important terms in our function. So we simplify this, and it's 1 over 3n to the, okay, hold on, this one here, it was 3n to the third. I didn't copy it right. So this is actually 3, and this is 3. So 3n to the third. Now that makes sense. So when you simplify, it's 1 over 3n to the 3/2. So p series, this is a p series, and p is 3/2, which is greater than 1, and we know it's convergent, but now you have to do the comparison. Okay, I'm going to say use limit comparison test here. That says if you take the limit and if the number is less than 1, then they both, let's go back to the limit comparison test and see it here. Okay, so you have two terms. A sub n is, so if you get a number c that's finite, that's all you need, positive finite number, then they both either convergent or both divergent. All right, moving on. Example 3. Sigma n e to the negative n squared, n from 1 to infinity. Now, if you look at this nth term, think about a function that corresponds to it. Instead of n, you put x e to the negative x squared. Well, that seems easy to evaluate, this integral. This is easy. to evaluate. How? I will use a substitution. U equals negative x squared, or U equals x squared. So, integral test. In a lot of examples, you can do more than one test, but this will be the most obvious test that we're mentioning here, the integral test. Example 4. I have sigma negative 1 to the n, and as soon as I see this negative 1 to the n, I'm thinking alternating series. Okay, so alternating series test. Okay, so that's quick. Example 5, again, we're not finishing it, we're just mentioning what strategies or what tests we're going to use here. The 5th example, I'm going to have in my series a factorial. So if you remember what we said, if you have a factorial in your nth term, use the ratio test. Okay, because it will be easy to cancel the factorial. Example 6. Here I have 1 over 2 plus 3 to the n. Again, there's more than one way to approach this, but I'm thinking about this series here. Compare with this one, which is geometric. It's geometric series, and we know when the geometric series is convergent. So I'm going to use here comparison test. Okay, we're going to compare it with this 1 over 3 to the n, which is geometric. Okay, and you can figure out what r is and so on. And this concludes this video.